Hi, this is Dthonn, and this is my presentation for my final exam for Data 605 Computational Mathematics for spring 2018. Basically, the assignment here was to take a look at some housing data off Kaggle, and then pick a dependent variable and an independent variable, the independent being y. So I did that. This section here is just loading packages. Here's where I'm loading the data. I'm calling it train 1. Take a look at that data. The attributes look like this. Just kind of a quick overview of that. If I look at set cap x equal to the greater living area, I saw kind of saw that there might be a good relationship there. Cap y is equal to the sales price, and then I plotted those. So I got a scatter plot. Looks like a pretty good relationship between greater living area and sale price. And this is greater living area, skewed to the right slightly, with somewhat normal skewed to the right. Sale price similar. We can see the ranges of the greater living area between 334 and 5642. That looks like it could be square foot. And then sale price 34,900 to 755,000 looks like dollars. So I want to see the probability of that data versus the quartiles. So x, small x, is the quartile at 0.25. So I want to look at the probability of cap x versus small x, or cap y versus small y. So I've done that here. Well, one other thing is I had captured the second quartile for the x value, small x, and then the third quartile for y to use in the table of counts, which we'll need because those are the values that we would be comparing there. But if I look at the quartile here at the 25% level, it's 1129. That's for the living area. And then if we look, so that would be within that range of 334 to 5600. And then similar with the price for the quantile of 25, the 0.25 level, it's 129,975. If I put that into the calculations, I look at the number of rows, take a look at put the data in there, and then take a probability of greater than x and sale price greater than y, and then divide it by the y quartile 1, it comes out to 0.871. So that's A, which is find the value of p cap x greater than x, cap y greater than y. Secondly, find the value of cap x greater than x and cap y greater than y. So I did the probability looking at the data, and then I put the calculations in here, greater than x and greater than y, divide by the total numbers in the data set, and the number is 0.653. And then thirdly, for px less than x, y greater than y. So they're opposite now. And similar calculation for that, and the number is smaller at 0.128 probability for that. So now we want to check independence. So I put set each variable to the data sets for the equations of living area greater than x, sale price greater than y, and then both together. Greater living area less than x and sale price greater than y. So I took the probability of each one and then the probability together, and then compared them. PAB equals, does it equal PAB times PB? And the answer is false. So it does not, splitting the data does not make them independent. And then the table of counts that we needed for the project was to look like this table here. So for that, I ran the calculations for each of those using the second quartile for x and the third quartile for y, and greater than or less than each one, and put those in different columns. And then the table looks like this below, where you can see the X values across the top, second quartile, less than or greater than, and then third quartile of Y on the rows, less than or greater than the third quartile. And then we have the probabilities of each of those combinations in this table. And then for the chi-square test, I took a look at the created a table with comparing X's and Y's. And this is the counts, this is probability, and then put it in a Pearson's chi-squared. The outcome of that was the p-value is a very small number, less than 0.05. So the null hypothesis is rejected, and the conclusion is that the sale price and the living rate of the greater living area are dependent. One's dependent on the other. So now to look at statistics, we took a look at some plots, derived some correlations, and then check the correlation of the pairwise set of variables as 0 at the 92% confidence level. So I took a look at the data together for X and Y, greater living area and sales price, and then plotted them here together. So you see somewhat of a linear relationship up to the right, and plotted X here as a histogram, and somewhat normal, skewed to the right. Y is again skewed to the right. And then I set up a model of Y versus X, and that's the residuals, good linear behavior there. And I took a look at the distribution of the residuals, and they are fairly normal. So I took a look at the training data and then looked at which attributes to put in my model. So here's a total of all the attributes there. So I picked from those. I selected lot area, greater living area, year built, and sales price, just as a best stab of something that would correlate to sales price. But I can see among these in the correlation plot that the greater living area has a good relationship to sales price. We saw that in the plot as well. And so I took a look at the correlations, and when you correlate with the t-test, the p-value is small again, and the sales price can be correlated to the living area. And this is the product moment correlation, and it shows that the correlation is not equal to 0, so that they do correlate as well. For linear algebra, I took the matrices above of that correlation matrix and just started with that. That would be a 3 by 3 showing, actually it's a 4 by 4 here, but it's showing the, everything plus the sales price. So I took a look at that, but the three I was looking at were the lot area, greater living area, and year built. And then took the inverse of that. That's the precision matrix that comes out as shown in this table here. And then multiplied the correlation matrix with the precision matrix, and it shows diagonals across for that. And then did the reverse, precision matrix times the correlation matrix. Again, it shows ones in the diagonals there. Decomposed first of all the precision matrix, so it's showing in the lower decomposition, everything is, all the numbers are in the lower, below the diagonal. And then took the upper decomposition there for the precision matrix, and then similar for the correlation matrix, decompose that to everything in the diagonals is 1, and then and below, and then the upper matrix below that. So the next section is on calculus, probability, and statistics. So the idea here was to get a model, a fit distribution, compare it to the data. So I took a look at that. I created a fit here, an exponential fit to the data, and then with a lambda shown as here, the lambda numbers there, and then just took the histogram of the function itself, which is the greater living area, put it up, placed it there. So we're comparing one to the other. So here's the model here below that, and that shows that it's not really the same. It looks a lot like the right side of it, but the other one has more of a normal look to it. skewed to the right, and this is just the right half of that. So it's not the greatest comparison there. And then let's look at some of the numbers to quantify that. We look at the 5 and 95% levels with the cumulative distribution function. So it goes between 77, and then if we look at the 95, it's at 45.39. So that's the range for between 5% and 95%, and that's based on the model. So, and then the real data is just looking at the quantiles, 5 and 95. It goes between 848 and 2466. So if we compare those, the model is a much wider range from 77 to 45.39. The data is ranging from 848 to 2466. Therefore, the model is not the greatest fit, and it encompasses a much wider data set. So the next section was about modeling. I created a model with the 4 factors here: overall quality, greater living area, lot area, and year built. And take a look at the summary of that model. P-value is very low. Adjusted R-squared is at 0.749, is a high value. It's a good value there. Took a look at the plot of each of these quality plots well, with a line through there. Shows kind of a somewhat linear greater living area. Has a good upward relationship. Somewhat linear year built as well. Lot area not so much. So wasn't the perfect model, but it had some factors in there that were pretty reasonable. And then I loaded that data from GitHub, put it up there from the test data, and then here's the equation from that summary above, showing all those attributes and the intercept and the coefficients of the attributes. I cleaned up the test data, ran a prediction on that, and it put some columns on there, and then submitted that. I prepared a submission for Kaggle, and then put some labels on there, and then I wrote it out and then submitted to Kaggle. So in Kaggle it looks like this. My score was 0.748. If I look at the leaderboard here, the perfect score is 0. Some people have submitted many times to get a 0 score. Various people have done that. My score is down here. So mine correlated somewhat, but I think there's more, obviously more to sales price than those factors. So I could hone that model, add in things like neighborhood. You know, obviously neighborhood makes a big impact on a sales price, which I didn't include. And there's a number of others. So I need a bigger model, more comprehensive, to get a higher score here. And that concludes my presentation. Thank you very much.